glad everybody could come out for the first colloquium spring semester. We're pleased to have with us today Hongying Shu of Hongying University. You see your title, and we look forward to hearing what you have to say.
Thank you, Dr. Robert. Okay, first I would like to thank Professor Xu for giving me this opportunity to introduce my work here. Today I want to talk about the bounded global Hopf branch for Nicholson's blowfly equation with state structure. Actually, this is the joint work with Professor Lin Wang and Professor Jianhong Wu in Canada. Okay. This talk contains 3 parts. I will first begin with my background and motivations, and then we will propose the Nicholson blowfly model with the state structure. In this part, we first investigate the stability of the positive equilibrium and the existence of locally Hopf bifurcations, and then investigate the property of global Hopf branches on the onset and terminate of Hopf bifurcations. And we will use numerical simulation to support our theoretical results, and we also observe the coexistence of multiple stable periodic solutions. And I will finish my talk with my conclusion. In 1954, the Australian entomologist Nicholson collected lots of experimental data on the sheep blowflies populations, and it observed the oscillatory behavior of these blowfly populations. Then lots of entomologists and mathematicians studied this experimental data, try to explain this phenomenon. So in 1980, Gurney first proposed the delay differential equation 1. First proposed this model, the delay differential equation 1, to explain this oscillatory behavior. And here Gurney used the n of t to describe the population of sexual mature adults at time t, and f is the birth function. So the derivative of nt means the change rate of the mature adults population. The f is the birth function, and this is the linear function, is the death function. So here choose the recurse type birth function. And here p is the maximum egg production rate, and 1 over alpha is the maximum population size. F is the birth function, and actually the death function is the linear death function. So gamma is the mortality rate of the mature adults. And here we have another parameter, tau. Here tau is the generation time, which describes the time taken from egg to sexual mature adults. It means if we use A to describe the age, then if the age A is larger than the generation time tau, it means the population should be mature adults, otherwise it's immature. This is the first proposed model to describe the blowfly populations to explain this oscillatory behavior. And then for this model, lots of mathematicians studied this model, and the dynamic behavior is very clear. Actually, the dynamics of this model are completely determined by the 2 parameters, the mortality rate, gamma, and the maximum egg production rate, p. And if gamma is larger or equal to p, it means the mortality rate is larger or equal to the maximum egg production rate, and then the trivial equilibrium is globally asymptotically stable. It means the species becomes extinct. And otherwise, if the gamma is less than p, and we find out another critical value, p over e squared. And if gamma between the p over e squared and less than p, and in addition to the trivial equilibrium, there exists a unique positive equilibrium, and this unique positive equilibrium is globally asymptotically stable. It means the population, the species population, will eventually converge to the positive constant level. And in the last case, if gamma is less than the critical value p over e squared, and in this case, the dynamic behavior will be more complicated. And Professor Junji Wei and Professor Michael Lee investigated this case in 2005, and they find out that in this case the delay can destabilize the stability of the positive equilibrium. It means that if we increase the time delay tau, and then we can find out the first bifurcation value tau naught. If tau crosses the first bifurcation value tau naught, the stability of the positive equilibrium will change from stable to unstable. And also find out that there exists an unbounded sequence of Hopf bifurcation value tau naught, tau 1 till infinity. And Hopf bifurcation occurs at this unbounded sequence of Hopf bifurcation value. And also they proved the existence of periodic solutions when tau is close enough with each bifurcation value tau naught. So this it gives the existence of periodic solution when tau is close enough to each bifurcation value tau naught. It means it explained the existence of local Hopf bifurcations, and they further investigated the existence of global Hopf bifurcations. It means that when the tau is larger than each Hopf bifurcation value tau I, and tau is away from tau I, and if we still have the existence of periodic solutions, and they further give the periodic solution still exists when tau is larger each bifurcation value tau I. Here and the Hopf bifurcation value is unbounded. It means like if we choose the first bifurcation value tau naught, for example, and the first Hopf branch from tau naught to infinity, so the global Hopf branch is unbounded from tau naught to infinity, and the second Hopf branch from tau 1 to infinity. And in this case, it's unbounded global Hopf branch. And this is the dynamic of this basic model one. But we can see for this basic model, Gurney does not ignore the moderation of the population during the moderation process. It means so we incorporate the moderation of the population during the moderation process, and we use a structure of PDE model, and this is the age structure, stage structure PDE model. We use the A of T and A to describe the population density at age A and at time T. And here the mu A describes the mortality rate of the population at age A. And here we choose the age-specific mortality rate. Tau is the generation time. So the death rate depends on the HA. When the HA is larger or equal to generation time tau, then the death rate is gamma, otherwise it's delta. It means for the mature adults, the mortality rate is gamma, otherwise for the immature population, the death rate is delta. And then we know the mature population, we use N to describe the mature population. So the mature population is equal to the population density, the integral of population density with respect to the HA from the generation time to infinity. And then we can calculate the derivative of NT and use the PDE method. We can find out lead to this delay differential equation with a delay dependent coefficient model to describe the Nicholson blowfly model with age structures. So this is our model, the Nicholson blowfly models with age structures. And you can see compared to the model, the basic model one, we only have one additional term, the explanation term. Yeah, the explanation to the minus delta tau. Actually, e to the minus delta tau is the survival probability during the moderation process. And also this explanation term leads to rather different dynamic compared to the model one. And in the following, in the next, in the second part, we can also notice that this additional term can lead to the coexistence of multiple stable periodic solutions. So next we will analyze the stability, the dynamic behavior of model 2. So our work is focused on the dynamic of model 2. So for the model 2, we first should got some preliminary results. The first, the positiveness and the arbitrarily boundedness of the solution under the with the non-trivial and non-negative initial conditions. This is the first result, and we can easily calculate the basic reproduction ratio R naught as given by this one. And also, when the basic reproduction ratio R naught is less or equal to 1, then the trivial equilibrium is global asymptotically stable. This is and otherwise, in addition to the trivial equilibrium, which is unstable, there exists a unique positive equilibrium and star. So next, we should analyze when R naught is larger than 1, basic reproduction number is larger than 1, the stability of and the positive equilibrium and star, and also the existence of Hopf bifurcation and the property of the Hopf bifurcation. And here I would like to mention that when the basic reproduction R naught is larger than 1, it means gamma should be less than P, and also we have a bounded of the time delay tau. So the tau is bounded by some number of tau max. So here tau is bounded. Okay, and then we focused on the stability of the positive equilibrium and also the existence of Hopf bifurcation. So as we know, we should analyze the root distribution of the characteristic equation. So we calculate the characteristic equation as given by equation 3. And as we know, the existence of Hopf bifurcation occur only if and only if there exists a pair of imaginary and values, and then we should analyze when the characteristic equation has a pair of purely imaginary roots. So then we obtained there exists a pair of purely imaginary eigenvalues if and only if S, the function S is equal to the function theta n at tau. It means the two curves of S and theta n have intersections. And S is given by this function, and theta n is the unique solution of this equation. And we can further investigate the property of S and theta n. We find out theta n is given by this graph. Theta n actually the blue curve is theta, the function of theta n, theta naught, theta 1, theta 2, theta 3, theta 4. And for each theta n function, theta is straightly increasing and continue down. And also we can find two ending points, 0 and tau hat. And the value of the function at two ending points is given by, we can calculate the value of theta n at two ending points. And also the red curve is the function of S and S tau. S tau is the first increasing and decreasing and also conclude down function. And also at two ending points, S is always equal to 0. So then the existence of a pair of purely imaginary eigenvalue only if S and theta n has intersections. So next we should investigate when S and theta n has intersections. We first obtained there exists a unique value C such that the derivative of S is equal to the derivative of theta n at C. And also when the time delay tau is less than C, then the S minus theta n is straightly increasing. Otherwise, when tau is larger than C, S minus theta n is straightly decreasing. And also we know at two ending point, S minus theta n, you can see at two ending point, S minus each theta n should be negative. So we got either S and theta n has exactly a pair of intersection or no intersection or tangent intersection at C. So we only have three cases for the intersect of S and theta n: a pair of intersection, no intersection, or tangent intersection at C. So no intersection it means non-existence of pair of purely imaginary eigenvalues. So non-existence of Hopf bifurcations. So this case, no Hopf bifurcation. And also in this case, a tangent intersection at C, we should further check the transversality condition. And actually, fortunately, we find out a geometric method to check the transversality condition. And we got the transversality condition can be determined by the sign of the derivative of S minus derivative of theta at bifurcation value tau star. And we find out if S and theta has a tangent intersection at C in this case, then the derivative of S minus derivative of theta should be 0. So in this case, the transversality condition does not hold. So this case, the transversality condition does not hold, and this case, non-existence of Hopf bifurcation. So for this case, also non-existence of Hopf bifurcation. It means the existence of Hopf bifurcation, we have two conditions. The first condition, the existence of purely a pair of purely imaginary value, and second condition, the transversality condition hold. So for this case, transversality condition does not hold. So the Hopf bifurcation occurs if and only if S and theta has an exact pair of intersection. So then we obtained this result. We proved that the Hopf bifurcation value come in pairs. As shown in this graph, the Hopf bifurcation value come in pairs. The first pair tau naught, tau 11. Second pair, this is the first pair tau naught, tau 11. The intersection of S and theta naught, and the second pair of Hopf bifurcation value is the intersection of theta 1 and S and S. Okay. So we got the first result, and then we give the stability of the N star and the existence of local Hopf bifurcation for the model 2. We obtained if gamma in this case is less than P or larger than POE square, then N star is asymptotically stable. And otherwise, in the last case, if gamma is less than POE square, POE square, and if S at C is less than or equal to theta naught at C, and then the positive equilibrium is also always asymptotically stable for any time delay. But if S at C is larger than theta naught at C, then there exists 2K Hopf bifurcation, local Hopf bifurcation value. So it means we have a finite even Hopf bifurcation value tau naught, tau 1 T, tau 2K minus 1. And also here, the smallest bifurcation value tau naught and the largest bifurcation value tau 2K minus 1 are stability switch. It means the way we increasing tau from 0 to infinity. And when tau cross the first Hopf bifurcation value tau naught, the stability of N star changes from stable to unstable. And for tau 2K minus 1, and when tau crosses the last bifurcation value, the stability of N star changes from unstable to stable again. So here we got the positive equilibrium is always asymptotically stable when tau is less than tau naught and larger than tau 2K minus 1 and less than tau max. And also, if tau between the larger than the smallest bifurcation value and less than largest bifurcation value, and then N star is always unstable. And for this result, we also mentioned the period interval of the periodic solutions when the tau is sufficiently close to each bifurcation value. So we also give the period interval of the periodic solutions. Okay, this is our first result on the stability of N star and also on the existence and the property of local Hopf bifurcation. Here I would like mention for this result we give the necessary and sufficient condition of the existence of Hopf bifurcation for these two inequality. And in this case, the dynamic behavior is rather different compared to the basic model. More specifically, we can see as we increase the time delay, the positive equilibrium will lose its stability from stable to unstable and undergoes a local Hopf bifurcation and a finite even Hopf bifurcation value. And also if we continue increase the time delay tau, and the positive equilibrium will regain its stability. It means this critical threshold should be the largest bifurcation value. And if we keep increasing the time delay tau and pass another threshold value, then here this value should be tau max, and then the positive equilibrium will be disappear. And the system only exists a trivial equilibrium, and in this case, trivial equilibrium is globally asymptotically stable. So it means in this case, the species becomes extinct. So it means for this case, tau should be larger than tau max. We only have one trivial equilibrium. And we also would like to mention for the first case and for this case. And in the second case, we find out there exists some tau bar. And when tau is larger than tau bar and less than tau max, we can further prove the global stability of the positive equilibrium n star. We can use two methods. One method by using Lyapunov-Lassa invariance principle and construct a suitable Lyapunov function, and we can obtain the global stability of n star. And we can also by use the method of monotone dynamic system theory, and we can construct a serious upper solution and a serious lower solution, and we can also prove the global stability of n star in these two cases. It means first case n star is globally asymptotically stable, and the second case we can find out there is some tau bar less than tau max, and here tau bar should be larger than the largest bifurcation value tau 2k minus 1. And here this is our first results on the property of the local Hopf bifurcation. And next we should deal with the property of global Hopf bifurcation. And by using global Hopf bifurcation theory developed by Professor Jianhong Wu, one of our collaborators, and we find out all global Hopf branches are bounded. To prove this result, it should be divided in 3 steps. So we first to prove all non-constant and non-negative periodic solutions are bounded. And second, we should prove the time delay on any global Hopf branch are bounded. And finally, we should prove the period of periodic solutions on any global Hopf branch are bounded. To prove the last step, the main idea, we should preclude the existence of tau period and 2 tau period and 4 tau period periodic solutions. So to preclude the tau period periodic solutions, it can convert to a one-dimensional ordinary differential equation. As we know, for one-dimensional ordinary differential equation, there does not exist the periodic solutions. So we can easily preclude the tau period periodic solutions. And for 4 tau case, we can use the Bendixson criteria or Dulac-Bendixson criteria to preclude like for plane system, it can convert to a plane system 2-dimensional ordinary differential equation using Bendixson criteria preclude the 2 tau period periodic solutions. But to exclude the 4 tau period periodic solutions, we should use the compound matrix and the general Bendixson criteria developed by Professor Michael Lee and Jim Madoni. And here we should additional condition this inequality. We require additional equation this inequality to preclude the 4 tau period periodic solutions. And after we finish these 3 steps, we can finish step 3, and we obtain all global Hopf branches are bounded. This is and then we reach to our main results on the property of the global Hopf branch. We proved that we obtained all global Hopf branches are bounded, which we already proved in the last slide. And also we proved each global Hopf branch connect a pair of Hopf bifurcation value, the first J Hopf bifurcation value and the last J Hopf bifurcation value. And also we mentioned the period of the periodic solutions on each global Hopf branch, the period interval on each global Hopf branch. And here we think we mentioned the main how to put our main results, the second main results. Each global Hopf branch connect a pair of Hopf eigenvalue, the first J bifurcation value and the last J bifurcation value. So we first should calculate the cross number at each bifurcation value. As we know, and also we know one idea. On each connected global Hopf branch, the sum of cross number should be 0. And we can calculate the first J Hopf bifurcation value, the first K Hopf bifurcation value, the cross number is always equal to -1, and the last K Hopf bifurcation value, the cross number is always equal to 1. So we should have even -1 and even 1, even -1, and plus should be 0. So we got this result. Any global Hopf branch must contain at least 2 Hopf bifurcation value, one from the first K Hopf bifurcation value and the other from last K Hopf bifurcation value. It means here we have two K Hopf bifurcation value. We can divide it in two. The first K Hopf bifurcation value and the last K Hopf bifurcation value. And for the first K Hopf bifurcation value, the cross number is equal to -1, and the last K Hopf bifurcation value, the cross number is equal to 1. So for each global Hopf branch, it should be connected at least one from the first and one from the remain part. And we can also, by using the continuity of Hopf branch, and also we already proved the non-existence of 2 top period and 4 top period periodic solutions. And we should also know that if we do not have 4 top period periodic solutions, and definitely we cannot have 4 top divided by n period periodic solutions. N should be equal. And then we can put the second main result. Each global Hopf branch exactly connect a pair of Hopf bifurcation value, one from the first J Hopf value and the last is from the last J Hopf value. And this is our main theoretical results. Then I will give a numerical simulation to expand our theoretical results. And here, this is our model, the Nicholson blowfly model with H structure. And we choose the parameter value, the set of parameter value is given by this one. I forget to mention the one. See here, M, which N is the population of mature adults. Actually, we have 2 functions. Also, the function of the population for unmature adults, but for this function, those 2 functions is decoupled, so we only need to analyze the one equation to find out the dynamic of the blowfly populations. Okay. And we calculate the basic reproduction are not larger than 1. It means we find out the upper boundary of the top max is equal to this one. And we can easily calculate there exists exactly 12 local Hopf bifurcation value, tau 9, tau 1, tau 2, till tau 11. And here we use the MATLAB package called DDE bifur 2. We can sketch each global Hopf branch. And here this is the global Hopf branch diagram. The horizontal axis describes the time delay tau, and the vertical axis describes the amplitude of the solution. It means the maximum NT minus the minimum NT. And we can see actually each curve is the global Hopf branch, and this is the first global Hopf branch. We can see it's bounded and they exactly connect the first Hopf bifurcation value and the last Hopf bifurcation value. And this is the second branch, connect the second bifurcation value and the last second bifurcation value. And the first branch, second, third, fourth, fifth, and sixth Hopf bifurcation value. And we can see each Hopf branch are bounded. And also here, tau naught and tau 11 are stably switched. So it means when tau is less than tau naught, the N star, the positive equilibrium is stable. And when tau between the tau naught to tau 11, the positive equilibrium is unstable. And when tau is larger than tau 11, and the SI is stable again. And here there is some top max. Top max, yeah, 270. So when tau is larger than tau max, the positive equilibrium will disappear, and we only have a trivial equilibrium. And this is the global Hopf branch graph, and we would like also know the stability of the periodic solutions on each global Hopf branch. On this curve, each point described a periodic solutions with this amplitude. Okay. So next we should analyze the stability of periodic solutions on each global Hopf branch. As we know, we can calculate the Floquet multiplier. When the principal Floquet multiplier is larger than 1, then the periodic solution is unstable, otherwise it's stable. So fortunately, we can use the DD5 to further sketch the principal Floquet multiplier associated with the associated principal Floquet multiplier. And we can see this is the principal Floquet multiplier corresponding to the first branch, and this is corresponding to the second branch, and third, fourth, fifth, and sixth. For this graph, maybe you cannot see clearly, and actually, from the fourth branch, the third global Hopf branch, from the third one, and the third, the fourth, the fifth, and the sixth, the principal Floquet multiplier is always larger than 1. It means the periodic solution on the last 4 global Hopf branch are always unstable, and but for the periodic solution on the first branch and the second branch seems different. If we amplify this graph, and we can got this graph, you can see this is on the first graph. Since we amplified, so maybe here actually can connect at somewhere. On the first graph, we can see at first the stability of periodic solution should be stable. So when we increase the time period tau at here, across the first critical value, the stability of periodic solution changes from stable to unstable. And if we continue increase the time delay, and cross the last critical value around here, and the stability of periodic solution changes from unstable to stable again. So the stability of periodic solution on the first branch should be stable, unstable, stable. And on the second branch, totally different. On the second branch, the periodic solution on the second branch, first it should be unstable, and stable, and stable, unstable again. So the unstable, stable, unstable again. And we can also observe that there are some intervals. You can see around 20 something or to 30 something. There are intervals, and such that the periodic solution on the first branch and the second branch, both of them are stable. And we choose the top. Here we fix the top in this interval, and we can sketch these two stable periodic solutions. And the left graph is the stable periodic solution on the first branch with slow oscillation, with larger period. And this one is the stable periodic solutions on the second branch with fast oscillation.
So the tau parameter, can you go back to the next stance? So the tau parameter you choose for two graph is reaching that part? You're pointing here?
Yeah.
And both graphs?
You will have two.
Yeah. Both tau values just choosing from that part?
Yeah. Yes.
Okay.
We fix the top.
Oh,
here.
fix the tau here?
Yeah.
Okay.
So we fix the tau in this interval, and actually at this interval we have 4 periodic solutions. You can see here around 25 we have 4 periodic solutions. We have 2 stable periodic solutions and 2 unstable periodic solutions on the third branch and the fourth branch.
So you are showing the 2 stable periodic.
Yeah.
Okay.
And here we've got the coexistence of stable periodic solutions. Even though we cannot get theoretical results, but at least we got some numerical results. And we choose the lots of set of parameters and always can get this result. And actually we continue further sketch the one of, as I mentioned, when tau is equal to 24, we have two unstable periodic solutions on the third branch and the fourth branch. And actually, we also sketched the two unstable periodic solutions on the third branch, and we find out this is the unstable periodic solution on the third branch. And we find out if we give a small perturbation on these unstable periodic solutions, and this solution will eventually converge to the slowly oscillating periodic solution on the first branch. And also we have the same results for the unstable. And also we have the same result for the unstable periodic solution on the fourth branch. So it means here we have two stable periodic solutions and two unstable periodic solutions, but we have small perturbation on the two unstable periodic solutions. Those two unstable periodic solutions will eventually converge to this one, to the slow oscillating periodic solution on the first branch. And here, we at least can numerically say that the Bayesian of attraction of periodic solution on the first branch may have a larger, more Bayesian of attraction. Okay. I will finally give our conclusion. And the first is the revised Nicholson blowfly population possessed a very different, very rich dynamic compared to the basic model. And also for this kind, the age structure, we cannot find any results for the previous work. And also somebody discussed use the data fitting. As I know, some professor in UBC in Canada, and they use the data fitting on the blowfly populations, and they told me you use this age structure, maybe more data fitting will be more perfect. And this is the first study to prove the global Hopf branch are all bounded, and we also point out the each global Hopf branch exactly connect two local Hopf branching value, and those lead to the coexistence of multiple stable periodic solutions. And I would like to also mention that during the proof, we mainly use the global Hopf bifurcation theorem and a general prediction criterion. And here we preclude. I would like to mention we preclude the existence of 4 tau periodic solutions. So we should require this additional inequality. We conjecture if this inequality does not satisfy, we still have our results. But here we have one open problem: how to preclude the existence of periodic solutions for high-dimensional ordinary differential equation. Like high-dimensional, I mean larger than or equal to 4-dimensional. Okay, and if you are interested in my work, you can refer to this paper in 2013. Finished. And thank you for your attention. And also welcome to visit Hongying University. At first, I never mentioned the Hongying University actually in Shanghai. So welcome to Shanghai.
That's a pretty small university. Is that all?
Sorry? Oh, this is the graph of my university. The main entrance.
It's like a small university.
This is the main entrance. Yeah. Actually, in China, the university is similar, different in South America, in America. Since in China we always have a main entrance, but here,
no entrance.
Yeah, we cannot find it. Yeah.
Just tell us how many students.
Everywhere is the entrance.
How many students?
Entrance is everywhere.
Like
Entrance is like
50,000
the face of the face of
50,000,
the
yeah.
university in
Yeah.
China.
Wow.
Okay, thank you.
Are there any questions?
You have, when you refer to equilibrium paradigm, can you measure how quickly the solutions approach that equilibrium?
When it's globally asymptotic, that's when you will.
So it's exponential?
Yeah, exponential decay too, yeah.
Yes, but can you identify the rate that it goes to the equilibrium?
We haven't.
You haven't
Yeah,
tried that?
yeah.
Because that would be interesting. These are the diagonal exponents
Yeah,
for the solution.
yeah, we haven't. Maybe we can do it later.
Okay.
Yeah, in the future.
Sure, okay. Why not?
Are there others?
Now, what is your, I know you gain the bifurcation solution, the periodical solution, the first one, and is the first one between the first one and the second one is unstable.
Yeah.
The last one between the most last one in the end, and also unstable, and in between stable, and in between is a stable. Now, what is your biological interpretation for that?
This is a lot of people ask me the same question. What should I? Biological explanation always the most difficult question for me.
But it's okay. How about what is related to the? Because it's related to the dynamics on the initial population. Now, the more important, I think, from the point of view, is that you how to identify your delay if you want to control it.
Yeah.
So now, when you surprise me is that when you doing your bifurcation stability analysis, so you basically use what kind of tool you use for analysis of the stability? You use the geometry way to approach that? How you show the bifurcation there's a stable oscillation? Actually, you get two types of bifurcation. One is a subcritical bifurcation.
Yeah.
Another one is a supercritical
Supercritical, yeah.
critical bifurcation. But what kind of tool you use to prove that? You use a
In the
geometry.
most case, we use the method proposed by Ferrer, Ferry,
Uh-huh.
and Hessa.
What method they use there? They use geometry approach, or what kind of method they use there?
I don't think it's geometrical method. It's a kind of the dynamic system, the method for dynamic system.
Okay, so you don't need to translate your system into the normal form, I agree. Do you?
Actually, here we do not calculate the normal form. If we should further determine it's a subcritical or supercritical bifurcation, we should calculate the normal form. But here we do not. Yeah.
You don't calculate.
For my project, we do not calculate if it's the normal form. We only find out. We focused on the global Hopf function. Since in the most case, only one case, the global Hopf function is always unbounded, like from tau naught to infinity. And here we proved there are some cases with state structure, the global Hopf function is bounded, like we have two boundaries. For your question, it's a kind of local Hopf function. Local Hopf bifurcation is non-global Hopf bifurcation. We should determine if it's supercritical or subcritical, determine the stability of the periodic solution when tau is sufficiently close to each bifurcation value. But here we don't need tau is sufficiently close to bifurcation value. Okay? Tau can be away from tau naught, away from each bifurcation value.
I know, because if you put it into the normal form, then you should be able to identify the period and also the rate of the conversion.
Yes.
Is that right? So, but you don't use...
Oh, the period we got.
You estimate, but looks like you estimate.
Yes, estimate. The period we obtain from the normal form.
Okay,
Yeah.
okay.
And also, I would like to mention one, maybe it's not such important biological explanation. Like I said, if the tau is large enough, and here I said I said if top keep increasing and pass another threshold value, the positive equilibrium will disappear. And the trivial equilibrium is global and symmetry will stable. It means the species will be extinct. So it means if the generation is large enough, so it means we should take more time to become mature, and definitely it should be decay to zero.
Extremely case easy to identify.
Yeah, but for the stability switch for those cases, I don't know how to expand the biological explanation. Yeah.
I take a look at your picture for the numerical. No, the next one. Yeah, this one. So from this one, you can see sort of bistable periodic solution.
Yeah. Since the
So
principle.
okay, so let me see.
Yeah.
Now, my first question is: do you know why the periodic solution bifurcated from the first bifurcation point, tau zero, just loses stability and then obtain stability again?
It's a difficult problem.
I just don't know. Yeah, it's just no reason.
And here, since here maybe it occurs some other type of application, but so far we cannot find any method to deal with this case.
So numerically, you just don't know.
Numerically,
Because numerically, you can calculate the Floquet
multiplier. Yeah, multiplier.
And then you can determine why the periodic solution lose its stability.
So
And
you
then
mean from the Floquet multiplier we can see something about the. Since here I think maybe, as my supervisor tell me, here maybe there are other type of application occurs. So
Okay. So then, I mean, in that part, you do have two stable
periodic
periodic
solutions.
solutions, which just coming from different bifurcation points.
Yes.
And the solution, I mean, they have different attachment domains.
Yeah. You have different attracting domain and different, and for on the first branch with the larger period, and the second branch is smaller period.
And that's, I mean, biologically, that's, I mean, really kind of interesting, you know? Because sometimes in biology, the population size, the population is subject to certain kind of uncertainty. The population is suddenly getting into another oscillation cycles, or just go to state. Yeah. So, I'm wondering how that happened.
So this project will focus on the math. Since the bounded global Hopf function network, so far that we cannot find any work. And also, one of my supervisor, Professor Jin Hongwu, he proposed the global Hopf function theory, and they only find out the unbounded global Hopf function cannot figure out the bounded global Hopf function. Since the global Hopf function, you have two cases. First case is unbounded, and second case is bounded. And so far we only have work on unbounded global Hopf function. So this is the first work on the bounded global Hopf function. So that's why we have this project.
So, to your experience, did you see any preliminary model has such kind of multiple stability, bi-stability of periodic solution?
I think so.
Oh, that's great. Thanks. Thank you very much.
Thank you again.